Lysozyme. One day, in his attempt to create a functional antibiotic, Alexander Fleming stumbled across something peculiar. A culture of bacteria he was working with accidentally got mixed with the patient's mucus, killing the bacteria. Surprised, Fleming took a closer look into the properties of the patient's mucus and rediscovered an antibacterial enzyme, lysozyme. This small step here eventually led him to the discovery of penicillin. Lysozyme is one of many different proteolytic enzymes found in the body's immune system. It acts as a key component in the body's first line of defense against bacteria, and it does this by hydrolyzing the cell wall of bacteria. Lysozyme is a hydrolytic agent, meaning it consumes water to break a chemical bond. Such bonds are naturally very hard to break, and as a result, lysozyme acts in normal enzyme function by lowering the amount of energy needed to break the glycosidic linkages of the bacteria's cell wall. But how exactly is this done? To understand, we need to look at the actual structure. This here is the lysozyme of hen egg white. It has two structural domains, one composed of alpha helices and the other composed of mostly beta strands. Together, they are able to produce a tertiary structure that binds to the peptidoglycan strands of the bacteria's cell wall. This binding is very specific, and the lysozyme moves along the peptidoglycan chain until the appropriate molecules are at its active site. Peptidoglycan strands are comprised of two main residues, N-acetylmuranic acid, or NAM, and N-acetyl-D-glucosamine, NAG. Together, they make a long-stranded polysaccharides via 1,4-beta linkages and create a very sturdy cell wall for bacteria. And it's this that the active site of lysozyme targets. Here is a close-up view of the enzyme's active site. Two amino acids play a very vital role here in breaking the glycosidic bond, glutamate 35 and aspartate 52. Together, they interact with NAM and NAD residues to hydrolyze the glycosidic bond. What we are looking at now is a mechanism that describes how these two amino acids work. Glutamate acts as an electrophile and donates a proton to the glycosidic bond. This allows aspartate to act as a nucleophile, and it attacks the carbon 1 of NAM, breaking the bond and producing a glycosyl enzyme intermediate. Note that NAM has been forced into a half-share conformation by the enzyme. It's really because of this unstable conformation that aspartate is able to be such an efficient nucleophile, since it provides enough space for a direct backside attack. Without this, it will be much more unfavorable to break the bond, and it's because of this conformational change that lysozyme is so widely used by organisms. Going back to the mechanism, after the intermediate is produced, water is finally introduced, and it acts as a nucleophile to attack the carbon 1 of NAM. This breaks the bond between the residue and aspartate, and it returns the enzyme back to its relaxed state. So now we understand exactly how lysozyme breaks the bonds of peptidoglycans, but why is it so important? Well, it all comes down to the bacteria's cell wall. Bacteria need a strong external shell, and without it, water will flow into the cell unchecked via osmosis. The cell will eventually burst, or lyse, from the internal pressure. Thus, if you can break the glycosidic bond between two residues, you can weaken the structural integrity of the cell wall and kill the bacteria. This lysing ability of lysozyme makes it incredibly valuable to the immune system. As a result, we find it in a lot of bodily fluids, such as tears, saliva, and mucus, where it acts as a first line of defense. Lysozyme is also highly abundant in the blood, since without it, bacteria could be transported anywhere in the body via the bloodstream. It should be noted, however, that while lysozyme acts as an invaluable part of the immune system, it's not the only part. Lysozyme is very effective against bacteria that have peptidoglycan cell walls, a subset known as gram-positive bacteria. This includes a number of genuses, from Streptococcus to Listeria. However, while still effective, it is less so with other bacteria cell walls made of other polysaccharides, and as a result, lysozyme is only one of many parts that make up the immune system. Still, it is incredibly vital to different organisms, especially newborn ones. Babies with too low levels of lysozymes have a much higher chance of getting lung diseases such as pneumonia. As a result, breast milk contains a very high level of lysozyme. It's also found in egg yolk and serves as a means of protecting the yolk from harmful bacteria, though harmful pathogens can still get in, so don't go eating raw eggs just yet. Overall, lysozyme is a very well-studied and understood enzyme. So much of what we know about proteins is because of lysozyme, making it an incredible enzyme indeed.
Created using Powtoon.